Hello, it's now the 5th of March 2022. I've just I ran across a video earlier today, and it was on the topic of Cantor's diagonal argument. Now this argument goes that, well, it's kind of like the original proof to why mathematics is incomplete, yeah. And there's no there are some questions you can ask in mathematics that can never be answered, and the proof was that there are some sets which contradict themselves in terms of definition. Like you could have a set that it includes all well, basically in terms of questions, you could have a set that includes everything including itself, but then how can it include itself? Yeah. Do you know what I mean? It's a bit like how do you put it? But I'll go through the argument. First of all, let's look at what Cantor's diagonal argument is about. Yeah. Give me a second. Right. So, in terms of Cantor's argument, yeah, it says here, in set theory, Cantor's diagonal argument, also called the diagonalization argument, the diagonal slash argument, the anti-diagonal argument, the diagonal method, and Cantor's diagonalization proof, was published in 1891 by Georg Cantor as a mathematical proof that there are infinite sets which cannot be put into one-to-one correspondence with the infinite set of natural numbers. Such sets are known as uncountable sets. The size of infinite sets is now treated by the theory of cardinal numbers, which Cantor began. The diagonal argument was not Cantor's first proof of the uncountability of the real numbers, which appeared in 1874. However, it demonstrates the general technique that has since been used in a wide range of proofs, including the first of Gödel's incompleteness theorems and Turing's answer to the Einstein's problem. Diagonalization arguments are often also the source of contradictions like Russell's paradox and Richard's paradox. I won't go into those, but I'll go into the original Cantor's argument, where you have a set of randomly generated real numbers. Real numbers are just numbers with decimal places on them, yeah? We'll say from 0 to 1, yeah? And every time you generate a random number, you write an integer corresponding to it, yeah? We'll go into the cardinal number thing. So if there's an infinite number of integers, there should be an infinite number of sets. He was trying to answer how many possible numbers are there between 0 and 1 in terms of real numbers, like 0.001, 0.012. How many could there be? There's an infinite amount, right? And how many numbers are there from 0 to infinity? Infinite amounts. So they should add up. So if you have one random number, two real numbers, 3 real numbers, 4 real numbers, up to infinity, there should be an equal amount. But then if you take the diagonal, yeah, of each randomly generated real number, yeah, so in the first position, yeah, I'll show you here. For example, here, you take the first diagonal and you add 1 to it. You take the second one, you add 1 to it to get your second digit. Now you're creating a real number out of the diagonal of a set of real numbers that goes all the way from 1 to infinity. Yeah. So you take the first digit of the first randomly generated real number and you add 1 to it. You take the second one, the third one, add 1, add 1, add 1, and you generate a new number. Yeah. So the first diagonal is 0, so that becomes 1. The second one, what they do, this is where the problem comes into it. This is how I solved it. When they go from 9, they go back to 0 when they add 1. When have you ever known 9 plus 1 to equal to 0? It doesn't. It goes to 10. That's how I solved it. Just it's basically just keeping in line with mathematics all the way. But when they get to 0 and they add 1, when they get to 9 and they add 1, they normally go back to 0. But that's nonsense though. 9 plus 1 is 10. 7, yeah, you add 1 is 8. So you get all these numbers, and then you write them out like you're writing a number after a decimal point. Yeah. So in this case, the number is 0. Yeah. 0.1108149110210. Now, obviously, this number is going to have more decimal places than the randomly generated numbers. Now, in this particular example I'm using, all my numbers go up to 9 decimal places. I generate these numbers randomly. Look, I can do it again. Let me generate them randomly. Yeah, watch the numbers. You see, random numbers. Now he's saying that if you add 1 here, add 1 here, add 1 here, write them as a number, you can never catch any of these equaling that diagonal number. And I'm saying I've got a trick. It's a trick. There is a way, there is a situation in nature where it can be. You could generate random numbers, yeah, in such a way, yeah, that you could go from 0 to infinity, yeah, and have the diagonal number included in one of those elements in that set, as one of those elements in that set. There is a way, and there are conditions. This is where it becomes a bit religious. The conditions are that the random numbers you generate, yeah, must run in a specific order. It's a bit like a chimp typing for eternity, and somewhere along the line it types out the complete works of William Shakespeare in the order that he wrote them in that moment. But that will have to be a moment, from 0 to infinity. The first time you try to go from 0 to infinity, you might not get it. The second time, you might try an infinite number of times, but there is one time where you try, where these numbers come up the way mine came up. Where they come up in such a way, yeah, because I can scale this up. I can scale it up, and you can see that it works, yeah, for any number. So this can go, this is 20 now, 20 different numbers, but this can go to infinity. But there are special conditions. So even if it does go to infinity, yeah, you still see that there is the second last number will always, yeah, this is that number written out like that, will always be equivalent to the actual number of the diagonal when written out. I have a special rule that I've developed, yeah, and that's what I'm trying to explain now, yeah. So in terms of that Cantor's argument, you can clearly see that this number, yeah, the randomly generated number, will have more decimal places, but up to 9 decimal places, it will always be equal to the second last number. So if this goes up to infinity, then infinity minus 1 will be that number that, in my situation that I described, that will be equal to the diagonal numbers plus 1. Yeah, obviously they started to apply this to binary and other things, but those are different bases, different systems of counting, and they also have different tricks. Yeah. Now, for you to get a situation that I've noticed, yeah, you would have had to have attempted to go from 1 to infinity an infinite number of times just to find that occurring naturally. Those of you who are sharp would have noticed it by now. This has 12 decimal places, but I'm only going up to 9. You can look at it and notice it, but it's a trick. I'm not going to reveal all my tricks now, am I? But you can generate it over and over again. Different numbers. These are different random numbers. You consider the different random numbers. Alright? Different random numbers. You can generate it again. Different random numbers. Yeah? And you can spread them out digit by digit, 0.62062 da 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 da. Different numbers, different real numbers, and all the time the second last number will always be equal to the diagonal written out as a real number, where the diagonal plus ones written out as a real number. But the last three decimal places you're gonna have to ignore. Yeah? If you ignore those, you get a hit. So if you get to infinity, an infinite number of things, then infinity plus 1, infinity plus 2, infinity plus 3 decimal places you ignore. So it does involve infinity plus 1 plus 2 plus 3. So he was right when he said that not all infinities are the same size. Yeah. So that's my proof there. For the religious bit, yeah, if this happens in nature, it will be a miracle. If it happens the first time, it will be a miracle. It's a bit at the settings of the universal constants. If it happened first time, that's a miracle. There have to be a higher being that's directing things for that to happen. Yeah, but there is a possibility, yeah, that you can generate a set of an infinite number of random real numbers, count the diagonals, add 1, yeah, and get one of the generated numbers to equal that diagonal, even though each number is getting touched at least once. The trick is to make sure you can count properly. When you go to 9, you go to 10, and the spare decimal places, you just ignore those. That's the proof.